Hello students, welcome back. We will be continuing our lesson. This is part 3. This deals with the testing the significance of difference between means. The objectives are: you will be able to learn how to perform a test of hypothesis concerning the difference between the means of two distinct populations using independent samples. You will be able to carry out numerical calculations for the problem. The learning objectives: you would be able to learn how to perform a test of hypothesis concerning the difference between the means of two distinct populations using independent samples. You would be able to carry out numerical calculations for this problem. Testing for population mean: when we have a single sample, we test whether the sample could have come from a normal population. This is carried out by testing a hypothesized value for the population mean. Suppose we wish to compare the means of two distinct populations based on samples drawn from them. The picture given here presents the setup. Here there is a population 1, population 2. From each population a sample is drawn. Population 1 and 2 have means and standard deviations. Samples 1 and 2 respectively are drawn from these population. Their mean and variance are shown with some suffixes. When mu suffix 1 means is a population mean for the population 1, mu 2 means the mean of the population 2. Here n 1 sample size of the sample 1, SD, S2, this is standard deviation of the sample taken from population 2. Our aim is to use the information in the samples to make statistically valid inferences about the populations. In this presentation, we would be interested to state whether the populations have same mean or different means. Now, I picturize this. There is a population, it has a mean mu. You are taking two samples, they are noted as sample 1, sample 2, they are coming from the same population. Now, the question is whether two samples have come from the same population, or we have this picture. First sample is coming from population 1, second sample is coming from population 2, population 1 has the mean mu 1, second population has the mean mu 2. Now, the question is whether the two samples have come from two different populations. These problems can be stated in the following form: if the two populations with means mu 1 and mu 2 are identical, we should have mu 1 minus mu 2 equal to 0, and if they are different, mu 1 minus mu 2 is not equal to 0. So, we have two hypotheses. As the first one has a possibility of getting rejected in addition to be able to fix a distribution form, this can be taken as null hypothesis. The other one is taken as the alternate hypothesis. A variation of this equal means problem: a sample of scores of students is taken from a population of scores of a class. The class average score is believed to be mu 1. After some training or coaching, a test is conducted and a sample is selected. Now, the average class score may be mu 2. Here we have two populations of scores. One is obtained before the training and the other one is after the training. A change in the mean values indicates the effect of training. If mu 1 is greater than mu 2, then the training has no effect. If mu 1 is less than mu 2, the training has some effect. So, we may want to test whether the difference in mean scores mu 1 minus mu 2 is 0 against mu 1 minus mu 2 greater than 0 or not equal to 0 or less than 0. The setup is null hypothesis. H is mu 1 minus mu 2 equal to 0 against the alternate one of the following. First row is k mu 1 minus mu 2 less than 0, second mu 1 minus mu 2 is equal to greater than 0, third one mu 1 minus mu 2 is not equal to 0. When population standard deviations are known, the test statistic is z equal to x 1 bar minus x 2 bar divided by standard error, where standard error of the difference of means is given to be square root of sigma 1 square by n 1 plus sigma 2 square by n 2. This statistic z follows a standard normal distribution, provided each sample size is large, that is n greater than 30. The population standard deviations are rarely known. In this case, we use sample standard deviation as estimate. Therefore, the test statistics is same, but the SG standard error has a change. Instead of sigma square, we are using the sample estimate. If the sample sizes are large, this statistics also follows a standard normal distribution. The limits are shown as per the previous slides. So, I skip this. Problem 1. To compare customer satisfaction levels of two competing cable television companies, 174 customers of company 1 and 355 customers of company 2 were randomly selected and were asked to rate their cable companies on a 5-point scale, with 1 being least satisfied and 5 most satisfied. The survey results are summarized below. The sample mean, standard deviation, sample size are given for both companies. Test at 1% level of significance whether the data provides sufficient evidence to conclude that the company 1 has a higher mean satisfaction rating than by company 2. So, the solution is we frame the hypothesis as before. H is mu 1 minus mu 2 equal to 0, k is mu 1 minus mu 2 greater than 0. We expect company first is more than company 2. The level of significance is taken as alpha equal to 0.01. The calculated test statistics value is 5.684. At 1% level, the critical region is the interval 2.326 infinity, and the test statistics falls in the rejection region. The decision is to reject H. In the context of problem, our conclusion is the data provides sufficient evidence at 1% level of significance to conclude that the mean customer satisfaction for company 1 is higher than that for company 2. Sample sizes are small. The test statistics is the same thing, z equal to x 1 bar minus x 2 bar divided by standard error, but the standard error formula changes. Standard error formula is equal to square root of s square bracket 1 by n 1 plus 1 by n 2, where s square is the variance of the pooled sample, that is both samples are combined. The formula is given there. This statistics follows a student state distribution with n 1 plus n 2 minus 2 degrees of freedom. A software company markets a new computer game with 2 experimental packaging designs. Design 1 is sent to 11 stores. Their average sales in the first month is 52 units with a sample standard deviation of 12 units. Design 2 is sent to 6 stores. Their average sales in the first month is 46 units with the sample standard deviation of 10 units. Test at 1% level of significance whether the data provide sufficient evidence to conclude that the mean sales per month of the two diseases are different. The null hypothesis is taken as mu 1 minus mu 2 equal to 0. The alternate hypothesis mu 1 minus mu 2 is not equal to 0. The estimate of variance of pooled sample is computed as 129.3. Now, the test statistics is calculated as z equal to 1.040. This value falls outside the critical region. This you can see here, reject, this is the region, this is the critical region. This critical value falls outside, that is within this region. So, the decision is not to reject H. The data do not provide sufficient evidence at 1% level of significance to conclude that the mean sales per month of the two decisions are different. Summary: the testing of the difference between two population means is undertaken. The cases of population variance known and unknown are considered. The procedure for large and small samples were provided. Two numerical examples were carried out to understand the testing procedure. Summary of the lesson: the mean of a population and the mean of the sampling distribution of x bar are shown to be equal. The variance of sampling distribution of the mean is shown to be smaller than that of the population. The testing of population mean is reviewed for large samples. The test procedure for the small sample is described. Testing of hypothesis on the difference between the two sample means was undertaken. Some numerical examples were carried out. We have come to the end of this lesson. It is hoped that you have learned some of the basic techniques of testing hypothesis. We shall continue and enjoy the learning. Thank you.